Hey, we are Group 2, and today we are going to talk about solid and elastic deformation.
We are going to explain the history of solid and elastic deformation.
And what solid and elastic deformation even means. And how to apply the equation to solve problems.
And how that equation can be applied into real-world scenarios. So, without further ado, let's learn some physics.
In 1655, Hooke was employed by Robert Boyle to construct the Brilliant air pump. 5 years later, Hooke discovered his law of elasticity that states that the stretching of a solid body is proportional to the force applied to it. Under these conditions, the object returns to its original shape and size upon removal of the load. Elastic behavior of solids, according to Hooke's law, can be explained by the fact that small displacements of their constituent molecules, atoms, or ions from normal positions is also proportional to the force that causes the displacement. According to Hooke's law, because a small increase in its length when stretched by an applied force doubles each time the force is doubled. Hooke's law laid the basis for studies of stress and strain and for the understanding of elastic materials. Hooke discovered the law of elasticity, which he first published in 1616. He published a solution in 1667 as the extensions of the force. He practiced his law on elasticity in his development of the balance spring or hairspring, which made possible a portable timepiece for the first time known as the watch. Although the first writings of the elastic phenomena occur in Hooke's writings, the first real attempt to construct the theory of elasticity using the continuum approach, in which speculations on the molecular structure of the body are avoided and macroscopic phenomena are described in terms of field variables, date back to the 18th century. Since then, a massive amount of effort has been focused on the study of the mathematical theory of elasticity and its applications to engineering and physics. Hooke's law states that the force required to deform elastic objects should be directly proportional to the distance of deformation, regardless of how large that distance becomes. This has brought us to the modern theory of elasticity, which is a generalized variation on Hooke's law, which states that the strain or deformation of an elastic object or material is proportional to the stress applied to it. Hooke's law is applied to elastic deformation because it is conventionally defined as a reversible deformation. Elastic deformation in metals commonly occurs in small changes in the shape of the atomic lattice. Such elastic deformation is linear and therefore obeys Hooke's law.
Firstly, let's clarify what deformation means. Deformation is a process of changing in shape through the application of pressure. The forces that act on a solid object affect the spacing of atoms within that solid. This may then change the shape and the size of an object. This is known as solid deformation. This change in spacing changes the external structure and size of the solid. As opposed to solid deformation, elastic deformation is a type of deformation that is reversible. In elastic deformation, the object will return to its original size and shape once the applied force is removed. Elastic deformation is given by Hooke's law that states that the amount a body extends is directly proportional to the force applied on it, provided the elastic limit of the object is not exceeded. Now, we can go ahead and discuss the equations for solid and elastic deformation. Changing the length of a solid is an example of solid deformation. Young modulus has a unit of force per area, which is N/m squared. Changing the shape of a solid is an example of elastic deformation. The shear modulus has the same units, N/m squared.
When looking at solid and elastic deformation, it's important to remember that there are two equations, and although they appear quite similar, they possess major distinctions. The equation for solid deformation, also known as the Young-Modulus equation, is expressed as F equals y times delta L over the initial length then multiplied by area, whereas the equation for shear deformation is F equals S times delta x over initial length, then multiplied by area. Keep in mind that in these equations, both y and s each have a variety of different values to choose from. You can choose the appropriate value depending on the material you are dealing with. Another key difference is the value of initial length. In the solid deformation equation, the initial length regards the length of the object parallel to the force. Meanwhile, the shear deformation equation regards the height or thickness. It's also worth mentioning that the value for the area is different too. The area for solid deformation is obtained by measuring the solid's cross-section. As for shear deformation, you can get the area by using the solid's surface area. Now that we understand the equations, we can move on to problem solving. Suppose you're asked to find the difference in length delta L of bone with mass being 22 kilograms, initial length being 0.35 meters, and area being 5.2 times 10 to the negative 4 meters squared. In this case, we can utilize the solid deformation equation and rearrange it to delta L equals force times initial length over y times area. Notice our solid is bone. Therefore, we can use the value 1.6 times 10 to the 10th. Before we plug in our numbers, though, we need to find force, which is mass multiplied by gravity. So 22 kilograms times 9.81 meters squared is 215.82 newtons. Now that we know force, we can plug in all of our values. 215.82 newtons times 0.35 meters over 1.6 times 10 to the 10th Newton meter squared times 5.2 times 10 to the negative 4 meters squared. Your calculation should give you an answer of 9.08 times 10.
Now that we understand how to use the equation of solid and elastic deformation, let's talk about its application to our everyday life. Well, without knowing it, you have seen many examples of solid and elastic deformation, and even performed deformation yourself without even knowing it. As a matter of fact, one of the examples we are going to talk about today are constantly in our day-to-day lives since the day we were born. This example is our bones. Now, every time we pick up an object with our arm, that object is described as mass times gravity, which is our force. And the length of our bone is described as L. These are all variables that fit into our equation of solid and elastic deformation. We further understand that even bridges with metal strings attached to it is yet another example of solid and elastic deformation. The ropes attached to the bridge can be described as our tension force T. Now, in this case, the metal that the wire is made out of is one of young modulus materials described. Now, one of the metals described is steel or copper, and steel or copper is what bridges are made out of today. The last example we will talk about is a type of solid deformation, more specifically shear deformation, which people have performed without even knowing it. If you ever laid a book flat and shifted it to the right, there are two opposing forces that go with that, and that distance can be described as delta x, and the area of the book can be described as a variable a. These are all variables used to solve for shear's modulus. Now, the three examples I have talked about is only some of the examples of elastic and solid deformation. I want to thank you for joining us and hope you gained a better understanding of the concept of solid and elastic deformation.